Get started. I'm not Arun Majumdar, clearly. I'm Gang Chen from Mechanical Engineering Department. Welcome to the mighty seminar series. And today we are great honor to have Professor Arun Majumdar. But before I introduce him, I would like to remind you the last seminar of this series this year is on May 5th. Again, we have speakers from Berkeley. You can see we have a lot of visitors from Berkeley. So it's the right time. Now I'm going to give a brief introduction of Professor Arun Majumdar. He received his bachelor degree from IIT Bombay and his PhD from UC Berkeley in AD line for research conducted under Professor Chang Tian. And on that, I want to put a footnote here. I joined also Professor Tian's group the same year, but we never met before that, and he graduated at the time I joined the lab. So really a great honor for me to introduce him. It's a great example. And he was a faculty member at Arizona State University and UC Santa Barbara before he joined the faculty in Berkeley in '96. And he currently holds Almy and Agnes Maynard Chair Professor in College of Engineering. He is also Associate Director for Energy and the Environment at Lawrence Berkeley National Laboratory, where he's creating a lot of new initiatives. So if you go to Berkeley, the Berkeley Energy Campus at both campus and also the National Lab, he is the person in the energy area. And Professor Majumdar served as chair of the Berkeley Nanoscience and the Nanoengineering Institute, and also was a member of Nanotechnology Technical Advisory Group to the President Council of Advisors. So that's the PCAST. And he served as the Council of Material Science and Engineering at DOE, and is a member of the Advisory Committee of the National Science Foundation Engineer Directorate. Professor Majumdar has received many awards and honors. I just want to mention a few. NSF Young Investigator Award, ASME Medville Medal, and Gustav Larsen Memorial Award, ASME Distinguished Alumni Award from IIT Bombay, and ASME Heat Transfer Memorial Award. And he is a fellow of ASME, AAAS, and also he was elected to National Academy of Engineering in 2005. With that, now it's Arun's turn to tell us his story in taking the science, what's going on at Berkeley, and in the efficient energy utilization.
Great. Can you hear me at the back? Great. Well, thanks a lot, Gang. Appreciate the kind introduction. It's been I met with several people today learning about the energy initiative at MIT. And really the highlight of a meeting was with all the students. And it was just amazing. I didn't know how 1.5 hours went by when I just talked to the students out here. And I think, and I could say that similar kinds of things are going on at Berkeley. And I think there's some interaction between the Berkeley and the MIT students, and that's wonderful to see. So I will talk, what I'll try to do in my talk, is there some, okay, so what I'll try to do in my talk is, okay, so I'm a professor and I'm a bureaucrat. So I'll try to give a little broad overview of what's going on in Berkeley bureaucratically, and then get into the science of what I do and what my students actually do. I don't do much, but my students and postdocs do in my lab, and all the collaborators that contribute to that. So I just want to give you a little sort of visual to get everyone sort of warmed up a little bit about the broader picture. This is, if you look at this map, this is the population density of the world. And we are over one of the concentrated population density, I think somewhere out here. I'm from here, and I'm originally from somewhere out here. So you can see that I've been always near population. But you can see where the big population densities in the world are. They're concentrated in Europe, somewhere in the coast out here. Huge population density in the Ganges Plain out here and in the coasts, and obviously out here, and some in Africa, et cetera, Indonesia, Japan, et cetera. It's worth looking at this because one of the major issues of energy is really population growth, because all the indicators are in terms of energy per GDP, carbon emitted per GDP. Those trends are all in the right direction. It's just that the population, per capita, everything is fine, but the population keeps increasing. And it's worth looking at this population and looking at the energy use. So this is sort of gives you an idea of where the energy is being used. It's a lighting pattern, obviously stitched together. But you can see the bright lights out here as an indicator where the energy is actually being used. And you can actually see the coastline, the Nile, and of course the energy, the lighting over here, and essentially dark over here. If you overlay the two, the contrast is quite striking. And you can now see where you don't have much population. That means you can't see the reddish or brownish, and you can see bright lights. And where you have the population, and these people out here really have not yet turned on their lights. And if they do turn on their lights, we have a huge problem in our hands. And the question is, how do we enable them to turn on the right kind of lights, if you may, metaphorically, and how do we reduce the lights without changing our lifestyle out here in the United States? That is the real big challenge, global challenge that we have. That's easier said, but in fact, if you get into the details, where the science and engineering and some policy comes in, is where the talk will go. Nevertheless, it's sort of, if you could look at it in a sort of using numbers. This is CO2 emissions per capita, and per capita is always a dangerous thing to do, because it gives you the average, doesn't give you the distribution. But let's, if you may, this is CO2 emissions per capita. This is GDP per capita, and as you can, this is, by the way, the average emissions around the world, because it's way below sort of the average over here because of these big population densities in India and China. But the United States is off the charts, and the question is, how can the United States come down? There is only one direction for it to go. It really has to come down. But the other big question is, this is a big question, how do we bring the United States at least to the average? But the question that often is asked is, which direction does China take? And if you look at all these, France is sort of flat because of nuclear, and the other countries are sort of almost in this line. Does China and India go that way, or does China and India go that way? And that is, again, which path it takes is a huge deal. And that is often, you can think of it as an opportunity for the United States, corporations and others to enable, and the United States government to enable the other countries go take the right path. Nevertheless, so this is sort of the big picture. Here is data from a paper which is more than 10 years old in carbon emissions, in the world. This is about 7 or 8 gigatons of carbon, or 24 or 25 gigatons of carbon dioxide per year, and that is increasing linearly. And that is essentially, it's going in the atmosphere. And if you can think of it this way, the lifetime is such that this is almost the lifetime of the CO2 molecule. There's exchange with the soil, with the oceans. The oceans are the big sink, but essentially a few hundred years. For all our practical purposes, it is being stored. It's a capacitor, it's being stored. And so if this is almost increasing linearly, carbon emissions per year, you can imagine where this is going. It's essentially being stored. It's nonlinear. It's quadratic, or perhaps that's the best estimate. And the big question is, how do you can think of as the Titanic hitting this iceberg over here somewhere. And the question is, how, if you can even get a glancing blow and turn the ship around, that would be a good news. Right now, we're heading right head on into this issue. So that's the big picture. This is IPCC prediction of what, if you want to stabilize at a certain concentration of CO2 in the atmosphere, what pathway we should take. And then, so this is carbon dioxide emission per year, billions of tons of carbon per year. This is year out here. Just to let you know, this is 2007. the area under the curve is the total carbon which has been emitted. And this area and that area are about the same, which means that in the next 50 years, we'll emit the carbon equivalent to all the carbon that we have emitted in the past. And so that's, of course, a big issue. And this IPCC prediction is an optimistic one. The reality may be actually worse than this. And so there, again, is a huge, huge issue. Given all this, the question is, okay, so are we reaching the oil peak, et cetera? And many people feel that, no, there's enough fossil fuel, there's enough oil around. Here is the price of oil, and here's the availability of oil. And the peak seems to shift with the price of oil. There is no fixed peak, because this is the amount of oil that we have actually used. This is in OPEC Middle East. These are all the other, and as the price of oil, remember there was at one point somewhere around $140, and then all this oil becomes available, becomes cost effective. So we're not going to run out of oil pretty soon. There's enough coal around. So here is oil reserves, Middle East. Asia is over here. If you look at coal, here is Asia, and here's Middle East over there. And the 4 big reserves of coal are USA, Russia, China, and India. If push comes to shove, people will be converting, coal to oil. These are all fossil fuels are convertible, and we have a huge problem then. So this is sort of the basic. These are known facts, and I think some of you already know this, but I just want to put it up in the beginning. This is the R&D funding in the United States, and it's worth noticing. This is the snake with which ate up a little pig. That's the energy in the 1970s, and we are, I think, over here almost going to relive the 70s, hopefully better than the 70s. This is defense out here. This is federal R&D, and this is space, and you can see the big space investment. This is healthcare going up over here, the R&D investment in healthcare. And energy has to go this way, otherwise we are in deep trouble. So hopefully now the administration is such that we might see some increase in the investment in R&D. The question is, how do we spend it? Where do we go from here? The way we're looking at it is the following. I mean, here is the flow chart, if you may, the energy flow diagram of the United States. The supply side out here, and this is the demand side, and here's transmission distribution. The supply side is, here are all the renewables out here, and this is nuclear. And these numbers are in quads. One quad is quadrillion BTU, or approximately an exajoule. And the United States primary energy supply is about 100 quads. So think of that number as 100, and think of these as percentages. So you got petroleum coming from domestic and net imports, natural gas, coal, et cetera. And you can see that solar out here is 0.006. The font is not big enough to really represent that number out here. I mean, if you look at this line, the line is sort of how much is there. It is so small. And for solar to grow and to even make a dent, it has to grow at an amazing rate. I mean, if you have a 35% growth of solar industry for the next 25 years, you will get to 6 quads. It'll be 1,000 times. And so we have an issue out here that is the current approach scalable, or do we need something even bigger than that? The wind and biomass hydroelectric is big out here. And the demand side, as I will talk about, is the residential and commercial buildings, and industrial, which is mostly heat and a little bit of electricity, and transportation. So I'm going to pick a few of these. I mean, of course, the challenge is easier said than done. The challenge is, how do we amplify this? How do we decarbonize that? And how do we reduce demand? And how do we create a transmission distributed interacts? Of course, that's the ball game, but it's easier said than done. And the question is, how do we do it scalably, cost effectively, economically, so that business actually grows, et cetera? And those issues are very, very complex because there are policy issues involved in that as well. So these are some of the Berkeley initiatives. I'm not going to talk about all of them. We are thinking the solar initiative. We are talking about a buildings energy initiative. I'll just give you a brief overview, and I'll insert some of the stuff that we are doing in this as well. Storage, carbon capture and sequestration, which I'll not talk about, but I'll be happy to answer questions in that. And these lighter ones are things that we are, There are people there, but we haven't quite formed a cohesive group, and we are thinking about that right now as we're discussing it right now. Should we not? And if so, if we should, who are the people who are going to lead it? For these, we have some people who are leading these efforts right now. And when I say Berkeley initiatives, these are fairly collaborative between LBL, Lawrence Berkeley Labs, and UC Berkeley campus, and all the collaborators that we have. So in the solar initiative, so this is what is now called the Helios program. And the Helios program, as some of you may have already heard about this, but let me just give you a little overview. It is essentially converting sunlight to a fuel. And there are many different ways of doing it. And after much debate, came up with 4 ways that we should pursue. We don't know which one's going to be a winner. Maybe all of them. Hopefully all of them will be. But here's the idea. There are 2 biological routes. One is cellulose, and the cellulosic route to producing hydrocarbons. And in fact, we're dropping ethanol or methanol right now. We're going straight to hydrocarbon. Engineered photosynthetic microbes. These are the 2 biological, and these are supported by 2 institutes. One is the Joint Bioenergy Institute, which is DOE funded, and the Energy Bioscience Institute, which is funded by BP. And these are separate, 2 different entities that are funding this part of it. And the other part is artificial photosynthesis and scalable photovoltaics to produce electricity, and using or photoelectrochemistry to produce a fuel, or splitting water, for example. And this is supported by DOE under Solar Energy Research Center. This is an example. That is, you have photons exciting carriers. If these carriers are separated in an inorganic material, and you have the right kind of materials at the end, perhaps you could use that to split water. So that is one project that is that is being focused. There's a lot of focus on this. And in fact, just last week, the new kind of catalyst came up where you could possibly replace platinum and use it using molybdenum, for example. And there's a lot of work going on with Jeff Long and others in chemistry. One of the things that we are doing with Rachel Siegelman in chemical engineering is to see if you can take molecules that would have enough of a barrier in between the molecular structure as such. They have enough of a barrier that can not only absorb photons, but actually charge separate with the same electrodes on both sides. And perhaps that could be a scalable way of doing it. These are very early stages. We don't know whether it's actually going to work or not. But we seem to have some success in this, but it's kind of premature to discuss in gory details. On the solar thermal side, and this is, as you know, has been going on for a while, got a lot of traction in the 70s, and then in the 90s sort of fell off the face of the earth. I mean, there's not much progress because solar thermal did not get much attention. But there are 2 kinds. One is the high temperature kind, where you have concentrator, and you have thermal storage, and then you run some kind of a cycle and to produce electricity, produce work, and then produce electricity. Or you have the low temperature flat plate solar collector. And this has been around for a while. The design of these systems depends on how the photon is converted. And primarily, these are converted to heat. So you can have a visible photon of about 2.5 electron volts. You get electronic excitation. And then you get phonons, which are emitted. And these are typically on the order, a time scale of a picosecond, right? So essentially, as far as the system is concerned, this is instantaneous heating. And we asked the question, and there's a lot of work still going on in this, and there's a lot of work needs to be done in improving these systems. We said, can we take it a different angle to this? That if we do this photo excitation, can we change this time scale beyond a picosecond or 10 picosecond? And one of the things that we're doing is with Peter Volhard in chemistry and Rachel Siegelman again, is to see if we can create a kinetic barrier so that you can then store it for years, if necessary. And then using a catalyst, reduce the barrier when needed, and do on-demand heating. So this is a different storage. And the question is, can this be done? And there are 2 students working in this. And the idea is to do it with an organometallic molecule which can undergo photoisomerization. So here is a molecule where upon sunlight, if you absorb sunlight, it converts into this state, which is a metastable state. with a kinetic barrier, which is high enough that at room temperature it stays like that. And you have to raise it to about 150 or 200 degrees Celsius for it to come back. Or in the presence of a catalyst, it comes back at room temperature as well. Now, of course, ruthenium, when people see ruthenium, that's, it raises alarms. This is not scalable. There's not enough ruthenium around. And it works for osmium. It works for ruthenium. It works for osmium also, which is in the periodic table, same column. And of course, osmium is not scalable as well. But right above ruthenium is iron. And what we're trying to do is to see if this molecule with iron replacing ruthenium can actually work. Because this absorbs sunlight in the sort of the blue to the UV, and we're trying to move it towards the greenish. And right now, with the iron, it does not have enough of a kinetic barrier. So we're trying to see if we can hang ligands over here to give it enough of a barrier for that to stay there. If it works for iron, then it's very interesting because it changes the system, because the collection, storage, and heat generation can be physically separated. Right now, everything has to be together, but they can be physically separate. So this has implications on the system itself. And this is something we're pursuing. We have sort of measured some of the values. They look very good, but there's a lot of work to be done in the molecule itself and to make sure and design it in such a way that it can store chemical energy and essentially become a solar fuel. So this is on the supply side. I'm sure many of you have seen this chart of carbon abatement, and I won't go into the details except to say that this has been categorized as the use of energy versus production of the supply side of energy and the management of carbon using forestation, et cetera. And what this says, this is the price of carbon the dollars per ton of CO2, and this is abatement in gigatons per year. And what this data really suggests, and there's a lot of questions about how McKinsey came up with this curve, but nevertheless, it gives you some indicators. And the indicator is that the lowest hanging fruit, think of this as the lowest hanging fruit, is efficiency. And it's not quite the supply side, but it's really on the demand side. And if you can use the energy more efficiently, or what we have, it goes a long way. And in fact, it could pay for many of the supply side. So in terms of efficiency, it's worth looking, where is the energy going? It has three big chunks. Buildings are the biggest chunk, 40% of the energy in the United States. This is the United States numbers. In other countries like, MIT works with Singapore. Singapore is like 60%, all right? Transportation in the United States is about 28%, and industry is about 32%. Industry is mostly cement, steel, glass, aluminum, paper, and many of them go into buildings and transportation. So, if you think of it as a life cycle analysis, buildings and transportation essentially hog most of the energy. So buildings really matter because it's about 10% of the GDP. 72% of the electricity, almost 3/4 of the electricity goes into buildings. So the grid is there basically for the buildings. And 55% natural gas. And today it is providing some grid level storage. There's a lot of talk about smart grid, et cetera. The biggest unknown in that is storage. And buildings are providing that today because you can turn off the thermostat for about 10 minutes, and you're not going to feel it because the thermal mass of the buildings are providing, enough of a, buffer for that. And if we do nothing today, if business as usual goes on for the next 20 years, let's say, we will have a 16% growth of electricity, which is an additional 200 gigawatts of electricity that we need to produce in the United States. And that will cost about $500 to about $1 trillion. Okay, of capital cost in power plants to produce the electricity, which is about $25 to $50 billion a year. Now, last year, that would have seen a huge number. Of course, today, 50 billion is nothing, right? But that's still a big number. And of course, this doesn't even, account for the carbon dioxide that is emitted. I mean, if you put a carbon price to it, that becomes, you can add some numbers to that as well. So these are big numbers. And I think it is fair to say that if we don't address the buildings, we're not going to address climate change. And so this is, and so the question is, what are the scientific issues? Are there only scientific issues? Are there other issues? So we have been doing, we have had a group in LBL which has been doing this for the last, 35 years or so. and there's a lot of wisdom associated with that. But there's some new things that are happening as well. And so we are thinking about this and I'll just present what we're thinking. So here is some legislation, which is Energy Independence Security Act 2007, which has said that there should be a zero net commercial building initiative. Why commercial building and why not residential? Well, there are about 100 million homes and 5 million buildings, commercial buildings. So if you want to go for the big energy hogs, you might as well go for the commercial buildings first, but not to ignore the residential. But let's say the commercial buildings, if this is 80% reduction in energy consumption, 5 times more efficient in new buildings, and at least 50%, twice as efficient in existing buildings. Existing buildings are much harder to retrofit and get it reduced because it's, if it's designed badly, there's not much one can do, but perhaps at least 50%. If we do this by 2030, or let's put it this way, if it were to happen today, the amount of energy that you will save is essentially you could eliminate the need for half the coal-fired power plants today. That's the magnitude of supply and demand. If it were to happen today, that's the amount of energy that you would save, and that's the electricity that you produce from the coal-fired power plants. And you could essentially eliminate half. If you take the rest of nuclear, hydroelectric, and other renewables and match up with the load out there, you would get a zero carbon footprint today, essentially zero carbon footprint today. That's the opportunity that we have. And of course, this is at a growth rate of about 1.7% per year, square footage. China is 7%, India is 8.5%. That's where the new buildings are really going. And there's a huge opportunity for these countries to leapfrog and design the buildings the right way and save energy. So question is, okay, so how do we do this? This is a humongous problem because we have 5 million buildings and people are not quite incentivized. So just to give you what the challenge is, it's great to have a legislation, but the reality, and legislators can say, we want to get to zero net energy building, but let's do a reality check of where we are today. So the most advanced buildings today are what are called LEED rated buildings, which are leadership in energy and environmental design, which are US Green Building Council. And I'm new to this field, and I was looking for data. I said, tell me, where is the data of actual energy use and of the most advanced buildings? And it was shocking to see where we are today. This is energy use intensity in kilobTUs per square foot. People still use kilobTUs, but nevertheless, per square foot per year. And these are the certified building, the silver rated, the gold and platinum. And maybe on this campus, you may have some gold or platinum rated LEED buildings. Okay, you don't. Maybe silver. But nevertheless, this is, as you go to better and better rating, on an average, you do well. Okay, you do better than what you were out here. And this average is lower than the national average. The national average is about 90, and you're at 51, 60. But look at the scatter in the data. I mean, there's no predictability out here. What is also interesting is if you take this data and take the ratio of the measured performance versus the designed performance of these buildings versus the design performance. Okay, so this is where people are designing these buildings, and here is towards the zero net energy goal of the legislation. All right? And as you go this way, you find that you do really badly. So you are at about a factor of 2.5 or 3 times worse than what you were designing for. But as you go this way, if you relax yourself a little bit, you actually do better than the design. Ideally, everything should be, if I'm an engineer, I would look at this and say that if it's within 20% of 1, I'm happy. But when it's 200%, then there's a problem. And the question is, why is this so? There are lots of reasons for it. But one fundamental reason is, and I'm an engineer. I never thought about policy. I've gotten involved in policy. Because if you look at where these buildings, everything is designed. All these building codes are for design performance, not for measured performance. And there's no requirement for it. This is the only big industry I know where people are building, delivering products of $1 trillion industry without any requirement for testing. There's no measurement. And that because there is no policy requiring it. So, and that's what you get if you don't have measurements. Because you design it and everyone washes off their hands, and you actually look at the utility data and say, oh my God, this is all over the place. And people don't know. I'll tell you, in Berkeley campus, Some of you may know this Corey Hall, which is electrical engineering building, Soda Hall, computer science building. And people go away at night, and everything shuts off. And at least some students are still there, hopefully. But people go away, and many of the lights are shut off. But the duty cycle is 90%. And we don't know where the energy is going. It's being wasted somewhere, and we don't know. And so there's some real gaps in today's field. There's some lack of measurement and policies requiring it. There's a fragmentation of the whole process of the design, build, delivery, operation. I won't go into the details of that. And there's a huge fragmentation of market. So let me just show you. So today's market, and we have to bring this into the picture in the engineering sort of design, is that you have companies which provide energy services. HVAC, windows and lighting. HVAC is Carrier, Trane, et cetera. Windows and lighting are Corning, et cetera, and lighting, Philips, GE. You have building materials from Dow, DuPont, on-site power, appliances, natural ventilation. You've got all these components out here. And these companies never talk to each other, all right? They never talk to each other, and their appliances, the systems, have no way of communicating. Except when they put it into a building, they are communicating, because they're all using energy, and sometimes they're fighting each other. So it's like driving a car with your brakes on, and it's wasting energy. And what is missing, first of all, is that this fragmentation, because no one is aligned towards a number, that you have to meet a certain, like if you have a computer, you have a certain gigahertz, you have to meet that performance. Or if you have a plane, you have to meet a certain performance, which is measured performance. There's nothing like that. So what is necessary from the engineering point of view is how do you do a system level integration of that integrated building design and operating platform, where you integrate physical science and engineering, architecture, information science and technology, where you get data, use the data to operate the building, and feedback control of the whole system. And it can get very complex, because if, let's say, you take a hotel, which is 1,000 rooms, and you got all kinds of things going on because people are going in and coming out, and you don't know exactly how to control it. So it's a very complex problem. And in fact, if you can measure the energy performance, even display it to the people, that feedback of people looking at the energy and where it is going could have a big influence. That's the behavior part of it as well. But the building operating system, sort of the Unix of the building, does not really exist. And that is something that people at Berkeley are thinking of. So can we develop essentially the operating system for both the design platform, and for the operation in a way that brings in the measurement and the operation into one unit? And that is something that we have gotten a lot of people in electrical engineering, for that matter, who were doing the SPICE and other software or tool development. They've gotten interested, and they started working with the people in fluid mechanics and thermodynamics, et cetera, to see, and controls, to see if they can develop this building operating system in an open way with companies along with us together, so that they can then take it and massage it and put shells around it, make it pretty. But the engine behind it does not really exist. And that is something that I think is very important. But it's also important to look at policy, because right now there is no policy for measuring. And in fact, I just testified about 2 months ago in front of the Senate, calling for a national standard for measured performance of these buildings, a number, so that everyone can get to that. But the influence of policy is very interesting. In California, this is per capita electricity consumption in California, and this is the year. And California has remained flat. Some of you may have seen this curve, and wondered how come. And this is the United States. Because there were 2 policies that were introduced. I won't go into the details of that. They're called decoupling policies, where for utilities, where the sales, utilities are inherently incentivized to make you more inefficient, because you will use more energy, they'll get more revenue, and that just defeats the purpose. So in the 1970s, they introduced 2 policies which decoupled the revenue of the utilities from the sales of energy, because they projected where it is going, and they said, if you could do better, you can increase the rate of the electricity rate of the ratepayer, and thereby you're not going to lose money. In fact, now they have decoupling plus, they can make money. And that innovation in policy went a long way in keeping the energy consumption in California about flat. And there were other implications also. That decoupling for buildings has not really happened. and that is what is required. So let me just then just move on a little bit, and I'm going to talk about certain sectors out here, and some opportunities for science and engineering. So let me pick on, I think I picked on the transportation side. And of course, the big thing in transportation is a combination of combustion engines and batteries and lightweight materials. But let me just talk about batteries, because in many ways that is sort of the more to be developed in the batteries area. This is what is called the Ragone plot, specific energy density, a specific energy or energy density in range of which correlates to the range of an automobile vehicle, and this is the power density, which relates to the acceleration. So if you look at where we are today, most lithium-ion batteries are about 100 watt-hour per kilogram, and what we really need to do is much more. So at least if you can get to about 200, 250, will be pretty, it'll be much better. But the gasoline energy density is typically around 10,000 to 15,000, depends on whether you use gasoline or diesel or others. That's the range, at least. That's the order of magnitude. And if your energy efficiency of your engine is about 20 to 25%, we're at about 2,000 to 3,000 watt-hour per kilogram, which is an order of magnitude higher than at least today's battery. But in batteries, it's not just the capacity, but it's also the cost. A Chevy Volt, the battery costs about the same as a car, or at least on the same order of magnitude, and that is not a scalable solution. Then cycle life, very important, at least has to be a few thousand. Safety, especially for lithium-ion, and these two out here. I'm going to talk about, in fact, we are looking at this very seriously in terms of this is certainly important to take today's lithium-ion battery and make it much more safe, increase the cycle life, increase the charging time, reduce the charging time, et cetera. But also, at the same time, what are the physical limits of energy storage in an electrochemical system? And can we approach these limits? How come we are, how far are we? It's like the Carnot. How far are we from Carnot? And that's very important to know. So if you look at today's battery, which is lithium-ion battery, graphite anode, certain cathode, the capacity doubled. These are typically consumer batteries. The doubling of the capacity is taken on an average about 16 to 18 years. I mean, this is not a Moore's law you want to follow. You have to really, we need some game changes out here. And so that's the progress in the energy density out here. That's a theoretical energy for this lithium-ion battery. And it's unlikely we're going to reach, this is the theoretical energy density. We're not going to compete with fuels, with fossil fuels. But there are other lithium batteries as well. These are lithium ion today. That's in fact, theoretical energy densities. You have, zinc air batteries, lithium air batteries. And there are some major issues about making lithium air batteries scalable and safe, et cetera. But the limit, at least, is about 5,000. So if you're at 50% efficiency, you are within the range of fossil fuel. The question is, how do you make batteries which are scalable, et cetera? And one of the things that I'll just give you this is not from my lab, but this is Nitash Balsara's, where he's looking at lithium anodes, but also looking at, if you make lithium anodes and you do several times charging, discharging, you have dendrites which form, and they short out the battery, so the cycle life goes down. And what he has innovated is a block copolymer in one block is polystyrene, which is extremely hard, and the other block is polyethylene oxide, which can conduct lithium. And if you put that together, you get essentially nanoscale channels for the lithium to flow, but the dendrites really cannot get through because it hits the polystyrene. And this has, of course, led to a company, et cetera. But the point is that fundamental understanding of materials at atomic and molecular scales combined with nanostructure architecture could really lead to some major advances. And I think we are just touching this in a fundamental way only in the last decade or so. I think there's a lot more work to be done in this area. Let me say a little bit about what I do in my lab. Is if you look at this whole energy landscape out here and ask the question, some cross-cutting question, you find that the energy conversion part of it, 90% of it is done via heat. And you would say, why heat? Because you pay the penalty of Carnot in heat. But you still do it. I mean, large gas turbines, et cetera. And the reason is that it's volumetric. And if it's volumetric heating, heating is volumetric, you could scale to larger power generation that you could not do. And fuel cells at the gigawatt fuel cell is going to be very hard. It's much cheaper to do it in a volumetric way using gas turbines and other kinds of, or steam turbines, for example. So 90% of the energy conversion today is by heat. So, and it's interesting to note that of the 100 quads that is supplied out here, 55 to 60 quads are lost heat. Okay, so, and the question is, can we somehow change the ball game and say that if you could convert just some number game, 10% of that, at 5 cents a kilowatt hour, that's a $70 billion per year, which could be harnessed. This is not an easy thing to do by any means. And there are many ways of doing it. And the waste heat comes out at 100, 200 degrees Celsius. Sometimes in some of the glass manufacturing and others, it comes out at 400 degrees, 300 degrees Celsius. And this is just being lost. And one could run, there are many ways of doing it, organic Rankine cycles and other ways of cogeneration. But I'll just give you one approach, which may or may not work, but it's worth at least attempting. And that overlaps very much with what Gang Chen and Rajiv and Millie Dresselhaus and all do, is using thermoelectrics. And this is a field which I'll talk a little bit about where we are in the history of this field. But as some of you know, this is, if you apply a temperature difference across a material, you get a voltage out of it. And these are generally semiconductors. And you can have them electrically in series and thermally in parallel. And you could use this as an engine, as heat engine, or refrigerant and heat pump, depending on what your application is. And the material of choice so far has been, over the last 50 years or so, has been bismuth telluride, which is a fairly exotic semiconductor. And it's expensive, and it's, the efficiency is low. And the efficiency depends on a figure of merit of the material, which is called ZT. It's a non-dimensional number. And you have the thermal power is Seebeck coefficient squared, electrical conductivity, temperature, absolute temperature, and thermal conductivity in the denominator. And you want to increase it, because the percentage of Carnot depends on ZT monotonically. And these materials, bismuth telluride, has a ZT of about 1, which gets you about 20%. And really, if you want to compete with other approaches, you need to have ZT of at least 2. System ZTs of at least 2. Material ZTs about 2.5 or more. That's sort of the thing. And so if you look at this material ZT of 1, each of these properties can be changed individually by orders of magnitude. You can take a semiconductor, dope it, and you can change the electrical conductivity by several orders of magnitude. So factor of 2 seems trivial. It actually is not, because of the fact that these are all interrelated. So here is what, if in a semiconductor, you have a carrier. If you change the carrier concentration, you can increase the electrical conductivity, make a semiconductor into a metal. You need electrical conductivity, but the thermal power goes down, and there's a peak that happens sometime, somewhere around degenerate semiconductor. The thermal conductivity, there are 2 components: the lattice part and the electronic part. So if you increase the concentration of electrons and holes, the electronic part increases, but the lattice part is sort of independent of it. And that's where you want to reduce this as much as possible. That's why you use heavy materials like bismuth and tellurium, et cetera, because your sound velocity is low, your thermal conductivity, lattice thermal conductivity is low. But these are all interrelated, so the electronic part and these out here. And these, S, sigma, and K, I call this the Bermuda triangle of thermoelectrics. A lot of people have gotten into it and haven't gotten out. And I think Gang, you and I and Rajiv, we are all in this boat right now, and we haven't gotten out yet. Maybe we should, but nevertheless. But here's where, so the question is why? Why are these interdependence? It all goes into the electronic structure. So if you take a metal, the Fermi level is deep inside the conduction band, and here are sort of the electron density of states. And if you apply bias, and you ask the question, which electrons are contributing to your transport? And you'll find they are generally near the Fermi level, near the chemical potential. And this distribution is a little bit asymmetric with respect to the chemical potential. And that asymmetry, okay, is where the Seebeck coefficient comes from. Anything that gives rise to asymmetry is good because you have higher thermal power. And I won't go into the math, but that's where it is. And so if you have a semiconductor with your Fermi level or chemical potential close to the conduction band edge, you've got large asymmetries just by the density of states. It increases very sharply with energy. And so you get large asymmetry, but you don't have enough electrons. The number of electrons is low. If you're way inside the conduction band, like a metal, you have a lot of electrons, but you have low asymmetry. So that's the dilemma. It really goes down to the electronic band structure, electronic structure of these materials. So that's the electronic structure, and there are two ways of manipulating it. One way is to make heterostructures. So you have metal semiconductor heterostructures with a band offset on the order of a few kT, and you can essentially create asymmetries. And there are other ways of creating asymmetry. The other way is creating quantum confined structures where you have all kinds of density of states, and you can, if you somehow tune it to have the Fermi level close to one of these big asymmetry points, you get a nice thermal power. And many of these came from here. 93, Dresselhaus and Hicks and Dresselhaus wrote a series of papers starting in the 90s, early 90s, where they showed that this could really lead to some very interesting changes in the S squared sigma of these materials. And so this is the sort of the history. You have bismuth telluride, which was invented which was discovered, sorry, in 1955. And there's a lot of, and this is just room temperature ZT. There are high temperature ZT, but never really crossed 1. And there was all these era which people came up with materials, but never really crossed 1. And there's no physical limit for ZT, but practically never crossed 1. And there was all the studies done, and eventually people made nanostructures and did find that many of them crossed 1. And they designed it not just for the electronic case, but for even reducing the lattice thermal conductivity. And bismuth telluride, antimoney telluride superlattices, quantum dots came from Lincoln Labs and out here. This is from Michigan State. Kenneth Zetas came over with these materials. And indeed, the ZT was higher. But in almost all the cases today, almost all of them, except for one exception, it was due to the reduction of K, the phonon. The lattice thermal conductivity went down. And the question is, why? Could be many reasons. And one has to go deeper then into the science of where this all comes from. And I'll very briefly go to it. Phonons are lattice vibrations. So you have atoms, you can jiggle them with a chemical bond in them, and you can create waves. So these are acoustic waves, and they're scattered from boundaries, defects, and there's phonon scattering. The spring is a little nonlinear, so they mix as well. The spectrum of this, the science of this is almost the same as blackbody radiation, and the spectrum of this is the Planck blackbody radiation with minor differences. So it is like a black body. So you can essentially use radiation theory to look at heat conduction. And the same laws, Wien's displacement law, et cetera, except for the fact that the speed of light and speed of sound are different by a few orders of magnitude. And thereby, this number is much smaller. And the lambda max at room temperature, it happens to be in the nanometer scale. So that's a length scale nature has decided. It's not for room temperature photon radiation, it's 10 microns. Well, in this case, it's about a few nanometers in phonon case. So you have to manipulate things at that scale if you really want to change the way things are done. So people in the past have been looking at alloys. So you take silicon and germanium, mix them together, and you get low thermal conductivity, or other materials, you get low thermal conductivity because you introduce scatters. But you have to remember that this is a broad band scattering. It's like black body radiation coming from the sun, and you're scattering, and you're getting scattering by atomic scale defects in this case, or by molecules, and you get blue sky. And that's one kind of scattering. And the question is, could we reduce even below this alloy, so-called alloy limit? And the idea is that, okay, so if you have atomic scale defects and you've got all kinds of black body radiation going on, you essentially get scattering by Rayleigh scattering, where the short wavelength ones get scattered much more than the long wavelengths, which is how we get blue skies. But the long wavelengths go through and give you heat conduction. And so the idea is very simple. The hypothesis was that, hey, can you introduce some clouds in the sky where you have particles in there which are nanoscale on the order of the wavelength, which are distributed randomly, and that can not only scatter the short wavelength, but also the mid wavelength now. And if the larger the size distribution, the better off you are. And so that was the hypothesis, and we collaborated with some folks in Santa Barbara. This is Art Gossard and his colleagues and his students and colleagues, and Rajiv and I are on this MURI. We're on this MURI together. And this is the material where you have, this is a test case. Indium gallium arsenide is a semiconductor. It's an alloy. And if you put in erbium arsenide nanoparticles inside, then you get all this randomness. The question is the thermal conductivity of this material lower than the matrix, which is an alloy? And indeed, that is true. And in this case, this was the first result. We reduced it by a factor of 2. Now we can reduce it by a factor of 4 and 5. And so indeed, that is true. And not only that, the electrical conductivity and the thermal power, the product of that, the S squared sigma, doesn't change much. In fact, you can increase it. And right now, the ZTs that we are seeing are higher than 1. And so that is something which was quite interesting. At least we could understand what was going on in these nano composite materials. We also then looked at, we said, okay, if this is the case, if semiconductor is the way to go, what is the abundance of all the semiconductors? And bismuth telluride is, of course, very exotic. Most people haven't heard of it. Of course, the most well-known semiconductor is silicon. And I think the MIT group and our group sort of came to the same conclusion. Let's look at materials which are abundant. And so we arrived at silicon and germanium about the same time. And so silicon is the most abundant semiconductor. It's also cheap. And we said, why can't we look at silicon? And bulk silicon is really bad because of the fact that lattice thermal conductivity is extremely high. But the mean free path of phonons is so large in these silicon materials. In silicon, it's at room temperatures about 400 nanometers, 300, 400 nanometers. And the electron mean free path is a few nanometers. There's a big discrepancy. So the idea was that if you could nanostructure silicon into wires or particles or so, you could reduce the thermal conductivity because the phonons will scatter off the boundary, and the electrons would not even feel the boundary because the mean free path is very short. So that was the idea. And so we collaborated with Peidong Yang, and we have a really strong collaboration, and where they did the synthesis and we jointly measured. These are some roughened wires, and these are some smooth wires. And there's a big difference we found. So this is how we measured the thermal conductivity of individual wires, and we measured electrical conductivity and thermal power as well. And what we found was the following, that if you take the smooth wires, these are the size dependents, and clearly the phonons are bouncing off the walls and the thermal conductivity goes down as you reduce the size. And this is similar to what Marcus Flick and others did at MIT, in fact, a long time ago. And so you have the size dependence out here. But if you roughen them, you have another additional drop in thermal conductivity. And this is very intriguing because what you find in these are crystalline wires. And this is thermal conductivity versus temperature. And you almost reach the amorphous limit. So almost getting a phonon glassy behavior in a crystalline materials. And we still don't know why. And there's a lot of questions being raised about this as well. And because of this low thermal conductivity, you find ZT on the order of about 1 in silicon, which is about the same as bismuth telluride. And that has raised, of course, a lot of interest. The question is, why is it going? And there's a lot of hypotheses right now, and we're testing them. So this is some theory which came out of Illinois, which predicted and which essentially suggested that there may be some correlated scattering going on in these phonons, which in the electron world has been postulated as Anderson localization. And the question is this really happening or not? And that is what we are testing right now. We're sort of going deeper into the science to see if there is this thing going on. If it is so, then amorphous limit is not the limit. It could go even lower because you're essentially canceling out the modes. That is something that we are doing, and we are sort of looking at the length dependence of the thermal conductivity. I won't go into the details, but essentially I'm just giving you sort of an update of where we are today. And we're doing not the etched nanowires, but doing electron beam lithography so that we can have well-defined lengths of these and try to understand, measure the thermal conductivity as a function of length. Because if we find an inverse length dependent, that means if the thermal conductivity goes down as we increase length, there's only one way that can happen, and that is some element of localization. And that is what we are going. let me, this is where the scientifically we're going. I gave an overall view earlier. Let me just conclude by an interesting article that I read at the turn of this century, which some of you may have already read, but it's worth noting because historically, we are in a very interesting time. It's my opinion. We're with an amazing time. I was telling the student, I wish I was a grad student again, because this is a time where we at least have a focus of where we should be going. Let me give you another historical anecdote, which is the following. At the turn of the century, there was a lot of discussion. What's the most important invention of the 20th century? And it's worth, when you're turning the century, it's worth asking that question. Because we think that in the 20th century, there were a lot of inventions and discoveries that have really changed the world. And the obvious answers are aeroplanes, nuclear, space, flight, computers, and all of them could qualify. And what intrigued me was none of these qualified. And that sort of, there was various studies and debates about this. And I looked at this and said, why not? And so here's some history. The history is that in 1898, there was a calling upon science to save the world from impending starvation, okay, by the British Association for the Advancement of Science. And in 10 years, in 1908, why? Because there was a growing population, lack of nitrogen in the soil, bacteria and biocatalysts were not sufficient. In 10 years, Haber discovered a catalyst that would combine atmospheric nitrogen and hydrogen to form ammonia, which became the precursor for fertilizers. The catalyst, the first catalyst, turns out was uranium. It was before the nuclear age, but it turns out uranium is a catalyst. In 5 years, Bosch at BASF developed, so this is the science, this is the engineering, and mass-produced ammonia, and again made fertilizers, etc. Why was this considered the most important? Why not those? Because this particular invention, the fertilizers touched humanity in no other way. Because the population grew, it saved the world from famine. The population grew from 1.6 billion to 6 billion in 100 years. Now, one could argue whether the benefits and all, but let's forget the ethics for the time being, okay? But this touched humanity in no other way, and of course, they got their Nobel Prizes, et cetera. But I think we are in that similar moment of history where the United Nations called the IPCC to look at what the issues are, and there was a calling upon science to save the world in some way from energy and environment. And I think we are in this period that we haven't quite found the Habers and the Bosches. And I think they may be sitting in this room somewhere. And I think that's where we are today. And I think in 100 years or 50 years from now, some of you guys, young guys, will be alive, will look back and say, wow, that was an amazing time where things fundamentally changed in Washington, D.C. I think that it's fair to say that's happening. And really things happen. So let me stop here, and I'll be happy to answer questions. And I hope this was, useful for you. Thank you very much.
I'm sure we have a lot of questions.
We have put some people to sleep.
Yes.
Yeah.
So why is the UK power consumption flat? They don't have nuclear that much, do they?
Don't know. Don't know the answer. You mean per capita?
Early on.
The CO2 emissions.
Yeah.
Good question. I don't know the UK. France is flat because of nuclear. That I know. I don't know why UK is flat. I'm not sure if it's flat. If it's flattish, it's less than the United States. But I don't know if it's really flat or not. I see. I don't know the answer. Yeah.
ZT alone won't do it. You need some ZT for cost. You looked at what that,
Yeah.
how close are the thermoelectrics, or where do you have to get those?
So there's a materials cost, there's a system cost, et cetera, there's packaging. I think it's fair to say that if you, instead of bismuth telluride, if you use silicon or silicon germanium, as Gang and others have done, the cost is significantly reduced because there's a material cost and there's a processing cost. And the semiconductor manufacturing today exists. And one could use that. So I think that is significant. I have a student who wants to start a company. I don't know why he's thinking along those lines, but he wants to start a company. And he has done, and this is not authenticated in any way, but he's done some cost analysis, and he's feeling that you could get about $1 per watt Now, dollar per watt is a very useful number to have because if you look at photovoltaics, they're certainly much higher than that. With silicon, I mean, this guy looked at it silicon based on our work. And I think, Gang, you might have the numbers. You're a businessman also right now, right? You might have the numbers for silicon germanium. And it's about the same?
I think dollar per watt is a good target.
So I think there's some positive things about doing it in abundant semiconductor materials. Yeah.
You mentioned at the beginning essentially a photochemical storage approach,
Yeah.
right?
This molecule,
yeah. So do you see, just generally, do you see this as essentially an escape from the Bermuda Triangle to go photochemical instead of thermoelectric?
No, it's a way to store it. You still produce heat at the end of the day.
Well, but at the end of a very long day.
Sure.
I mean, the mechanism, of course, is very different from the mechanism involved in the regular thermoelectric.
So thermoelectric is only converting it to electricity, but you're still storing it as a chemical fuel, and when you need it, you convert it to heat and then to electricity. The interesting question, actually, I mean, just...
But you probably would never use the same kind of mechanism for doing so that you would use in thermoelectric materials, right? Because, of course, you have the heat in a very different form, and there would be all sorts of ways you could convert that to electricity that wouldn't involve materials like silicon, germanium alloys, or
Right, so you have energy stored in a very different form. I won't say heat is stored, but the energy is stored in a very different form. The question that we are, so I did some work in the 90s in Santa Barbara, where if you have, so let's say you have chemisorption on a surface, okay, and you have a heat of adsorption, and you ask the question, where does it go? I mean, you got 3 EV. If oxygen dissociates in platinum, you got 3 EV, okay? That's a lot of energy for heating. And we found that energy, that chemical energy, first goes to create a hot electron. And that electron decays down to produce phonons. And that's what we call heat of adsorption. Okay? And we actually showed that if you make a Schottky diode with a thin enough metal, you can capture the electron and produce electricity. We call it chemicurrent. And I think similar things could be done out here if you store it in a chemical bond. And if you unwind it and excite an electron somewhere, you could collect the electron and produce electricity where we don't have to go through the heat route anymore. And thereby, you're not limited by Carnot. So that's something that we are thinking of. There's a lot of things to do. So, yeah.
So what are the issues about solar thermal conversion? Because as you said, 10 or 20 years ago, that was a pretty hot topic.
Yeah.
You would expect that maybe the efficiencies you could match photovoltaic elements or something like this. Right?
Well, yeah, I think there are some experts out here who can tell you, yeah. It's not just the efficiency, but the cost also. Cost could be today solar thermal is more cost effective than solar photovoltaic, right? Just dollars per watt, it is more cost effective. The question is, okay, so if you look in the future and the cost of photovoltaics are coming down, will it become better than solar thermal? Don't know. Okay, that depends on how we innovate in photovoltaics. But today it's better. Yep.
You're talking about thermochemical storage there. What kind of specific energy storage data do you see that achieving in terms of, you're talking about lithium air reaching 5,000 and the current liquid fuels have 10,000 watt per kilogram.
1 hour per kilogram.
Yeah.
Approximate. They're actually higher than that.
What do you see the thermochemical?
Not as high as chemical fuels. I mean, the photoisomer is about, well, it's actually quite substantial. It's 1.3 EV. So you can now look at the mass of this, and I haven't quite converted, but it's quite substantial, 1.3. Now, there are other photoisomers, by the way. There are lots of photoisomers. Why not use those? It turns out this one absorbs partly in the visible, and it can store and the whole energy is about 2 point something. Part of it is half of it is kinetic barrier, and half of it is stored. And that stored part is substantial. And that's why this gets interesting. The other photoisomers don't store it as much.
Question. You mentioned at the start carbon capture, and there were some efforts going on that. Maybe you can tell us a little bit, just the overview of what you're doing.
Well, I can tell you a little bit. The biggest cost is in capture, biggest risk is in sequestration, right? So let me talk a little bit about the science part. I mean, when you capture in carbon dioxide, well, for carbon dioxide, there are only two chemistries that are, actually three, but let me just talk about the two predominant chemistries that are known. One is the uphill reaction of photosynthesis, and the other is a downhill reaction of bicarbonate. Okay, that's it, right? Most of the capture, biocapture is photosynthesis. All other capture is done by bicarbonate formation. That bicarbonate formation has some rate-limiting steps. And there's some very interesting science you could do for catalyzing that to enhance the speed. And we have catalysts in our body, carbonic anhydrase, can reduce the barrier and induce the reaction faster. How can we emulate, I mean, could we create catalysts to have higher turnovers? That's a science question. That's number one. If you form the bicarbonate, you have to react with something, either some amine or some sodium or calcium. Once that bond is formed, you have to heat it to break it, right? So depending on the strength of the bond, if it's ammonium bicarbonate or some other amine-based thing, the bond is weaker, you can use waste heat from a coal-fired power plant to do it. If it's calcium carbonate, you need really high-grade heat to do that. So there's, the science issues of how the chemical bond is, how do you tune that chemical bond has huge implications on the system, on the capital cost and the operating cost of heating, et cetera. So those are the issues for the capture, and that's the 80% of the cost today, 70 to 80% of the cost. So that's what we're dealing with. On the sequestration side, right now, there's a shortage of carbon dioxide in the United States. I don't know if you know. There's a shortage of carbon dioxide in the United States because there's no pure carbon dioxide except from natural sources. And they use it for enhanced oil recovery, et cetera. So right now, people are buying carbon dioxide and putting it down there. And really, no one is monitoring it that well as to where is it going. There's a lot of simulation that needs to be done of groundwater resource, where and what kind of reactions happen. So there's a long way to go in that, both the risk side, the policies of it. Okay, if there's leakage, who pays for it? And all those issues are open right now. And I had a chat with some students today who seem to have thought through some of these issues. And, but the capture part is a technological issue. I think if you can reduce the cost of that, that's a huge opportunity. A lot of industries are looking at that right now.
Let's thank our speaker again.
Thanks a lot.